Hi everyone and welcome to my presentation on Scikit-geometry for the virtual SciPy 2020. My name is Wolf and I work at a company called QuantStack in Paris and Berlin. And you can find me on GitHub and Twitter. And at QuantStack we do a lot of scientific open source. For example, we are involved with maintaining many of the Project Jupyter things. So for example, we help with the IPy widgets library, the BQplot library. We are writing JupyterLab extensions, and we have also released the JupyterLab debugger last year. We are also involved with XUS, which is a library to create Jupyter kernels. And you can find the XUS SQLite kernel and the Python and C++ Cling kernel online. And one project that we're really excited about this year is called MAMBA, which is a fast re-implementation of the Conda package manager. And that implementation uses C++ and is a lot faster than Conda. You can also use our XTensor, NixSIMD, and XFrame frameworks for C++ that re-implement NumPy and Pandas in C++ and are easy to combine with Python, R, or Julia. And we also have a very small robotics branch, which is basically me and an intern, and that has developed this Scikit-geometry library last year. So what is computational geometry? Computational geometry is the study of algorithms that can be stated in terms of geometry. And the challenge is to develop efficient algorithms and data structures to solve problems that can be stated in terms of basic geometric objects. And one specific task, especially for computational geometry, is always the accuracy versus speed. For example, if you have a small floating point error, then maybe your parallel lines actually do intersect somewhere and so on. So that's something that we need to take care of. And some use cases for computational geometry are robotics, for example, motion planning and map building. You have geographic information systems to do route planning or extract information from maps, computer-aided design, integrated circuit design, where you might do shape description and component placement using these algorithms and things. One of the most powerful libraries for computational geometry is Seagull. That's a library in C++ and comes with some Python bindings that are based on Swig and not very Pythonic. And now we have come up with Scikit-geometry, which is bindings to Seagull. And it's using PyBind 11, which is a great library to connect C++ and Python code. And Scikit-geometry also comes with a bunch of helper functions for drawing geometric objects. Now, how do you use Scikit-geometry? Scikit-geometry brings a couple of primitives that you can use to do computations. So one of the basic building blocks is obviously the point 2 and the point 3. Those two are the fundamental objects, and from them you can create a segment, array, or a line in 2 dimensions, or you can also create a vector or a circle, an isometric rectangle, or a bounding box, and in 3 dimensions, planes, triangles, and polyhedrons. So now I'm going to demonstrate a bunch of these entities and the functions attached to them. So here I'm importing Scikit-geometry. So here I'm importing Scikit-geometry and the draw functionality from Scikit-geometry, and I'm creating a point, and then I can print this point. So I have a point created at 0, 5. I can create another point just like that, and I can draw the first point, and now I can draw the other 2 points at the same time using the Matplotlib backend of Scikit-geometry. I can also print the values of one of the points, so I'm printing x and y here, and it's 0 and 5, and I can print the type of x, which is a special Scikit-geometry number type, which is easily converted to a float in Python, but it's a type that has a multi-precision formulation, so that results are more precise than otherwise. Here I'm importing Scikit-geometry and the draw function, and I can create a point and I can print this point. So I see it's a point at 0 and 5 in 2 dimensions. I can create another point and I can draw the first point, and I can also draw both points at the same time. And as you can see, it's at 0 and 5 as expected. I can check the values with x and y accessors, and I can see it's 0 and 5. And I can print the type of x, and it's a special number type, which is not a regular Python float, but easily converted to one. And this is a multi-precision floating number type that Seagull and Scikit-geometry internally use for very high precision operations. Now I can create a vector from those 2 points by using the constructor from 2 points for the vector. There are many other different constructors that you can find in the reference, but this is the one from 2 points. And now I have a vector that goes from A to B, and I can print this vector, and I see, okay, it has some value, and I can draw this vector. So it goes from the origin to -1 and -4, as expected. I can also create the vector, for example, by algebraic operations. So if I do 1 point minus another point, the result is a vector, and I can draw both vectors now. And this vector points into exactly the opposite direction as the other one, as expected. And I can scale a vector by some constant factor, for example, by using the multiplication. Or I can add the vector to another vector and get 2 times that same vector in this case, because I'm using the same one. Or I can compare the equality of vectors. And here we can see a line. So I'm creating a line that goes through A and B and stretches from -infinity to +infinity. And I can print the parameters of this line, and I get A, B, and C, the line parameters for the line equation. A segment is a line segment which has a start and an end point. So here I'm creating a segment from A and B, 2 points, and goes from A to B. And I can also ask for the supporting line, which gives me the same line as before. And I can ask for the minimum point and the maximum point. And I can ask for another type, which is the direction here, that gives me something which has no length, but just points into some direction. You can also ask for the bounding box of a segment. And I can draw the segment and the bounding box, and I can see, okay, this is the bounding box of the 2 points in the segment. I can create bounding boxes of multiple points, for example, to get just the axis-aligned bounding box here, and so on. You can ask for a ray. So this is a ray that starts at A and points into the direction of B. A ray is basically a line that has a start point but no end point. Or I can also create a circle like this, which has a point at the center and the radius. I can also ask for an intersection between 2 segments, for example, or intersections actually between many other entities. So, for example, one of those 2 could also be a line, etc. And in this case, the result of the intersection query is another point here right in the center. But it doesn't always have to be a point. It can also be a segment. For example, if I intersect one segment with itself, the result is the same segment. You can also ask for the distance between objects, and in Scikit-geometry as well as Seagull, you usually ask for the squared distance. So in this case, I get a 0.8, which is the square of the distance between this point and this here. And this reason for using the square distance is that not taking the square root of something yields better accuracy as well as better performance, obviously. And it's enough for many applications to use the square distance to compare, for example, the distance of different objects to each other. So you don't always need to take the square root. You can also create transformations and apply them to your entities. So in this case, I'm creating a rotation with 0.5 radian. And in this case, I'm creating a translation by some vector here. Then I can use my segment and I can apply the transformation by using the dot transform operator. And if I do that, I can see that my values have changed and I can draw this. So here I have this blue line that is translated by 3 and 3, or I can see that I have this blue line here, which is rotated around by some degrees. So this is the basic functionality. Now I'm quickly going to talk about the installation of Scikit-geometry. So to install Scikit-geometry, it's best to use MAMBA, obviously, but you can also use Conda. If you want to use MAMBA, you can do Conda install MAMBA-C CondaForge, and then MAMBA install Scikit-geometry-C CondaForge. If you want to use Conda, just replace Conda MAMBA with Conda. You can find the docs online and the source code as well, and it's all on the LGPL license. More advanced functionality. Let's talk about polygons. Polygons are pretty interesting for many applications. So here I have a small helper library to load SVG files. And I have a small helper function to convert that SVG file into a Scikit-geometry polygon. And here I'm loading a polygon from this SVG file that I have here. And I draw it in Scikit-geometry and I get this. And now I can ask, and this is for the type of this P1 and the polygon, and I can do some stuff on it. For example, I can iterate over all the vertices, which yields me 0.2 entities. And I can iterate over all the edges, for example, and I get segment 2s with the 0.2s from before. I can ask for the orientation. I can ask for the area. I can ask whether a polygon is convex or concave. I can check whether it's simple, so whether it crosses the border or not of itself. I can ask for the coordinates, and now I get all the points, but it is a NumPy array. So I can reuse this NumPy array to do other operations using NumPy. And here I'm loading another polygon, P2, and I draw P2, and it's a hexagonal thingy. I can reverse the orientation of the two. I can draw P1 again, and now I'm going to do the Minkowski sum. The Minkowski sum basically takes the other polygon, P2, here, and slides it all over the boundary of P1 and creates the sum, which looks like this. So this can be used, for example, for offsetting polygons and other hopefully interesting applications. Now I can also compute something that is called the straight skeleton of a polygon. So for this, I'm just calling this function to compute skeleton. I have a small helper function to draw the skeleton. And now I can create a drawing of the straight skeleton and the polygon P1. And as you can see, we can use the straight skeleton to inset or offset the polygon again. So in this next example, I'm going to show how to offset the polygon using the straight skeleton. This is the next series straight skeleton. And you can use interact from SciPy widgets here to create the slider. And as you can see, I can just do these kind of operations pretty easily using Scikit-geometry to grow or shrink a polygon using the straight skeleton operation. We can also do Boolean operations on polygons. So here I have two polygons in blue and red, P1 and P2, and I can join them together to create one polygon. I can compute the intersection of the two, or I can draw the difference. So remove the one from the other. These are all very handy operations for many applications. Another very handy thing is to compute the convex hull. So here I'm just going to get a bunch of random points, and I draw those random points, and I compute the convex hull using the Graham-Andre algorithm. And doing this yields me this polygon, this outer polygon, which is a convex hull of all the points in the center. Now for polygon simplification, we can use the polygon simplification algorithms implemented in Scikit-geometry and Seagull. So here I have a function to generate a random polygon, and I can use the random polysimplify function here, which is using the Scikit-geometry simplify functionality inside. And I'm creating an interact widget again. And using the seed, I can generate different random polygons. And now I can select the amount by which I want to simplify. The more I simplify, the fewer vertices will my resulting polygon have. But the lesser it will represent my original polygon. If I go all the way to 0.9, I have a very good representation of my original polygon, but many vertices. You can also do multi-polygon simplification using these functions here. So here I have multiple circular, more or less, polygons, and I can simplify them like this. And I can also select the topology preserving simplification. And now Scikit-geometry, or rather Seagull, will try to really preserve the topology between those polygons, which is interesting, especially if you are doing applications and you have something like height lines that you don't want to actually cross each other. We can also create arrangements in 2 dimensions from lines and polygons, basically. So here I'm loading another file, arrangement.svg, and I create the Scikit-geometry arrangement. And now I'm inserting all the elements from the SVG into my arrangement. And I can draw this arrangement like this. And it's basically just an outer polygon and a bunch of lines and segments here and some sort of other polygonal hole. And now I can do something that's called computing the polygonal visibility. And this is pretty useful in robotics, for example. So you can compute from this point that is here in pink, what other edges and lines pieces can I see. So here I get the result of this query, and now I again made some interact sliders for this. So it's easy to play around with this a little bit and change the position to see how the visibility changes depending on where you are. Now, how can we integrate Scikit-geometry better with NumPy? In this case, I'm creating a bunch of random segments, and then I vectorize, using np-vectorize, the intersection function from Scikit-geometry. And I'm drawing all the random segments like this. And now what I'm trying to do here is to compute all the intersections between all these random segments that I have. And for this, I can now use my vectorized vintersect function here that will broadcast this over all of the combinations by using this syntax here. So that's pretty classic NumPy stuff. And now I have all the intersections here, and I can extract them by using the lower triangle or upper triangle. And I can plot them using the Scikit-geometry functions, and I see that all these colored dots are my intersections. One other function that is included with Scikit-geometry at this point is a Voronoi diagram. So I'm just generating a bunch of random points, and I can create the Voronoi diagram from this, like that. And here I can draw this Voronoi diagram, and I see that, yeah, just as it's defined, you have this beautiful Voronoi diagram. And Scikit-geometry also has some features for 3-dimensional queries and entities. So here I'm loading a teapot from an object file. And I have some functionality here to plot this, and I can draw it then. So this is loaded into Scikit-geometry as a 3-dimensional vertices and objects. And I can plot this with matplotlib, and I get this teapot. And now I can create something that's called an AABB tree. And I can check for intersections whether this segment in 3 dimensions intersects with my object here. And I get for the do intersect query, I get the fast result that yes, it does. And I can check for all intersections of the segment with my object, and I get the precise locations of the intersections. Now that we've got a pretty good overview of what Scikit-geometry has to offer, we can compare it with other Python libraries for doing geometric algorithms. And the main competitors, I would say, are Shapely, which is based on the Geos kernel that was extracted from Postgres. It has pretty good support for polygons. It's a very GIS-focused, I would say, kernel. And it doesn't really support infinite entities like lines or rays, and it doesn't support 3 dimensions at all. And I'm not sure, but I don't think it uses multi-precision numbers internally. Now we have another pretty awesome library called PyGeos, which was made by the GeoPandas devs, and it has similar limitations like Shapely because it's also based on the Geos kernel, but it has a very nice vectorized API, and it's very easy to use it with NumPy. So that's very good. And then there's Scikit-Special, which is a fairly unknown, I think, library. It's very Pythonic, and it was implemented purely in Python. And it has pretty good bindings to NumPy. It has a few nice basic types, but it doesn't have all the entities that we have in Scikit-geometry. And it has fewer advanced features. and Scikit-Spatial actually cannot handle polygons. There's another library called PyClipper, which is based on Clipper, which is a C# and C++ library. And it can only handle really polygons and not much more, but it does handle polygons very well. And it has functions to do joins and intersections of polygons or outset computations of polygons. What is some future work in Scikit-geometry? So things that we might want to add are splines and arcs and ellipses, which are not currently well supported using Scikit-geometry. And it would be cool to add in a constraint solver that I'm going to talk about in a few seconds. We would also like to further the integration with NumPy and the rest of the Python scientific stack, and maybe expose some functions using Xtensor or using other means through Pybind 11. And jumping over the C++ to Python barrier is kind of difficult, so that's something that we are interested in tackling somehow. And one question is, for example, is it possible to actually have a geometric kernel that is JIT compilable? So maybe if the geometric kernel would be implemented in Python, we could have some JIT accelerations that we currently can't have because our kernel is implemented in C++. So now I'm going to switch over to Adjacent, which is another library that we've been working on and that we've put under the umbrella of Scikit-geometry. Adjacent is a geometric constraint solver library. So I'm not sure if all of you are familiar with what a geometric constraint solver library is or what it does, but it basically, if you are familiar with CAD, computer-aided design programs, then you might know that you can construct these kind of sketches by adding constraints to your sketch. So saying that this line is parallel to this line, this point is coincident with this other point on this other line. And then you might have a perpendicular angle here, some other angle there. You might have some constrained length here. You might have a tangent here or concentric circles, etc. So Adjacent is a pure C++ port of the NodeCAD C# library that has an internal constraint solver. It has Python bindings through Pybind 11, and it's currently a work in progress, but it has some promising first results. And I really have to say that this code has been very much inspired by NodeCAD, and all props to them. So they have really figured out how to do this kind of stuff. I'm going to demonstrate you the Python interface here briefly. So we can import all the adjacent entities here. And we have some conversion functions to Scikit-geometry for the drawing, mainly. And now we can create basically symbolic points. So I can create a new point for adjacent by using this small helper function here that creates a point with a bunch of parameters. And then I can create a line between those points, or I can create a circle with a certain radius. I can print those entities. And now I can create a sketch where I add those entities. And I can also add some constraint. So here I'm adding a constraint for P2 and P4 to be coincident. I'm giving a constraint for the circle to have a certain diameter. I'm adding more coincidence constraints. I am adding a length constraint, and so on and so on. And I can update this, and then I can draw it. So here I have basically the result of what I wanted. I have the concentric, no, not concentric, but I have this point being in the center of the circle. Circle has a certain diameter. I have this point being in the same spot as the other point for this other line. So this works very well. And now I'm just doing a small dynamic interactive widget here where I have pretty much the same arrangement of constraints, but I do have one difference, which is this angle here that I'm setting. And I'm also setting the line to be tangent to the circle. So I can create this drawing. And now I have computed the solution to these constraints for some values. I can do the same again for different values, and I can change the angle here, and it will change. So I'm not sure exactly how this is going to be used, but I think it's pretty cool to have an API like this available from within Python itself. And if we can integrate this further with Scikit-geometry, I think this will be a very powerful thing for many different applications. for example, for drawing applications or sketching applications, etc., etc. So one other topic that I promised to talk about is generic programming in Python, and I had some ideas that I think would be useful for Scikit-geometry, and I wanted to present them here because I think they might find an interested audience. And so what I would like to achieve, at least for Scikit-geometry, to be more compatible with different ways of basically doing JIT optimization, for example, is to have a class, a base class that is parameterizable, so that I can make a point of different number types. So if we look at C++ or Julia, and especially Julia is winning, I guess, some brain power from Python developers, then those two things have in common that they have a pretty good static type system that Python kind of has, but doesn't, because really Python is doing a lot of duck typing. But I found one way to achieve a little bit of static typing inside of Python, and I wanted to present it. And so how would you write a point class in C++ or Julia? So in both cases, you would probably use a struct like this, and then you template it with a type t, and you make sure that all of your points are with the same number type of t. And then once you instantiate your point, for example, like here, you can specify that you want your point to have a float 64 number type. And you can have a function that also constrains these number types. Same for C++, you have this class f, for example, which would you template your number types. And then you can instantiate your point using, for example, the double number type, etc. So this works pretty well in C++ and Julia. So how could we do that in Python, and why should we do that? So what's good about it is that type member variables are very useful for optimization, because they allow you to basically dense pack your structs, and they give you fully typed methods. So if you implement this operator plus, and you know exactly the type of your left-hand side and right-hand side, you can perform very optimized operations on those numbers. And you still keep the flexibility over which number type is actually used with the library user. So the user can decide the trade-off between speed and accuracy. With data classes, we can achieve at least a typing and force typing of all of our member variables. So in this case, we can say that you have a x that is a float, and then you have some default value. And we can also easily in Python implement the plus operator. But here we cannot really enforce any types at runtime or compile time. I mean, at compile time we can, but at runtime we cannot. And you can see that this implementation of a point works, and you can also do the plus. Now, if we want to generalize this and try to create a generic class out of this, then we would probably want to use from typing this generic type, and then use the type for t as a template type, so that we can implement our point that inherits from the generic type of t. And then our data members are templated with this t as well. So we decide at implementation time basically that our point will be a float or of some other number type, for example. And still we can implement our add function here like this, self and RHS. That those could be typed, but right now they aren't. But in check type, we can raise a type error if our types do not match the way we like it. And then we return from self underscore class this regular addition basically. Now, some of the magic that will happen that will allow us to write things like an instantiated meta class basically is in this class get item, which is invoked before the init function to figure out what actual type we are going to take. And so what you can see here is that this is a class get item, so this is not a regular get item. And the get item, the class get item here, will get a type variable as the item. And that allows us to instantiate a point of some sort of float, rational, or whatever. And here we're using a small cache to retrieve our type from cache if we have it. And otherwise, we will create actually a new type based on the arguments that we get to this class item and put it into the type cache. So here we are creating a new Python type, completely new Python type, based on point, using the same functions and all of that. But actually it is a point with some concrete types added to it. So for example, we could create a point of floats, or we could create a point of integers, etc. And then we enforce the types for our member variables in the post-init function, which is also a basic data class function that is executed after the initialization of the member fields. So here we have, we go through each of the data class fields, and we make sure that our data class field has the concrete type that was chosen for this field. Okay, so I will show you now how this actually works. So for example, here we have a point, and then we template it with float, which gives us, oh, sorry, I have to execute this. So this gives us, so here we can use the class get item with a float, for example, to get a new class that is a point of floats. We can do the same, for example, with a bool, and then we get a new class which has the point of bool type. And now I can instantiate one of those points, and even though I'm instantiating them with integers here, which is different from a float, they are casted in the post-init function to floats, so that here I see they're actually floats. And they can check that too by doing the p1.x and check that it's a float. You can do the same with bools, for example. Now each of those integers is cast to bools, false, true, and false. And I can use my regular add function that I implemented to add 2 points of floats together and retrieve another point of float, because I'm using the self __ class method in my add function. So this allows me to do something pretty similar to what you would do in C++ or Julia for templated types. And here I can see that if I have 2 points of floats and I do a division operation on them, and I divide 1 by 10 here, because I implemented a division operation up there that divides each of the elements, and I print the result, I will see that I have actually an inaccurate result, because floating point numbers cannot represent all numbers equally well. And 0.1 is one of those numbers that is basically not actually 0.1, it's 0.1 point, and then a lot of zeros, and then something. So that's not great, because this is not an exact result. And one of the solutions that are possible to solve this is to create a point of a fraction. So fraction is one of Python's types that can be used to show or to calculate with fraction numbers. So here I'm creating a point of fraction, and I just initialize it with the same integers as before, but there's a conversion operator basically implemented for the fraction constructor, so that if I put in a 1, it will be a 1 divided by 1. If I put in a 10, it will be 10 divided by 1, etc. So this works fine. And now I can create another point, and then I can divide those two again using the same operations implemented for floats. And I see now that I have actually an exact fraction of 1 divided by 10 here, as well as 10 divided by 1, etc., etc. So this is a way to basically implement a very nice way of enforcing types on data classes. And I would hope that we could use this in the future to maybe, for example, even do something really crazy, which would be to compile Python to C++ and get generic classes in C++ and reuse them as C++ library. This could be something that Serge Guelton, who is the author of Python, could look into, I guess, if he finds time. And we could also, try to transform a generic of T to a template class of T in C++ and generate new class definition. And we could hook this idea up with Transonic and Python, two awesome JIT libraries. And yeah, and we should definitely also look into adding in multiple dispatch, which is one of the other core features of Julia, into this entire idea. And one other like cool trick that we can do using this is now we can import from SciPy the simplify and use these different constructors here. Now the SciPy expressions are basically translated from the string here, but also integers are just simplified as integer expressions. And I can again use the plus operator to even like do a plus on this and get SciPy operations. And I can now use the numbers that are inside of my classes and do SciPy operations. So I can, for example, compute the derivative for x of z, and it will just work. So I think that is pretty cool, and it's a way to do something similar to expression templates in C++.